So thanks for inviting me to speak to you all this morning. So I've done a lot of work over the last couple of decades, I suppose, on increasing extreme weather hazards around the world and how they're linked to climate change. Just to tell you first a little bit about the basics, and I'm sure that a lot of you know this already, but we've been increasingly emitting carbon dioxide into the atmosphere as humans over the last 150 years or so, but certainly increasingly over the last 50 years. And we've got measurements of this since 1958 from Mauna Loa in Hawaii. And carbon dioxide is the dominant greenhouse gas forcing that matters when we're talking about global warming. And that means that it has specific properties that enable it to actually absorb long wave radiation emitted from the Earth's surface, and to actually, that would normally be emitted to space, and therefore it increases the temperature of the Earth. And we're talking about quite large increases in carbon dioxide now, much higher than we've seen in the last 600,000 years. And you can see on the right there a plot showing the carbon dioxide concentrations in the atmosphere for around the last 600,000 years. And you can see that during the pre-industrial period, it was around 280 parts per million, and it's never really got above that level until quite recently. And it reached its maximum level in June 2020. So each year it goes up a little bit more because of the carbon dioxide emissions we put into the atmosphere. And it's around 418 parts per million at its maximum in June this year. So we're putting more and more carbon dioxide into the atmosphere. That's directly linked to global temperature, global mean surface temperature. And this is how they managed to set the targets for the Paris Agreement, the 1.5 and 2 degree targets that you can see on those arrows there. And the important thing to understand about carbon dioxide is that it's not, I suppose, the rate at which we emit it that matters, it's the cumulative total, because carbon dioxide itself has a lifetime in the atmosphere of around 100 years. And therefore it matters how much we emit every year, but also it matters that total that we emit, and that will affect the anomaly, the temperature rise globally. And you can see there that we provide the report, the special report on 1.5 degree of warming, looked at these potential pathways for us to reach these targets of, say, 2 degree warming by the end of this century, and what carbon dioxide we could actually emit to do that. And you can see there's quite a linear relationship there between carbon dioxide and temperature rise. And just to say that that's where that also where I suppose the comment that's been picked up in the press comes from, that we've got around 12 years left, or potentially only 12 years left to reach, to try and reduce our carbon dioxide significantly before we start to reach these cumulative totals. I've all seen this as well, which is the warming stripes diagram from Professor Ed Hawkins. And this really shows quite dramatically the change that we've seen in global mean surface temperature since 1850. And you can see that that's got 2019 in there as well. And you can see some big El Nino years coming in with natural variability, but really you can see that signal coming through in recent years. And actually we've seen about 1.1 now degrees of warming since pre-industrial times. And remember that the Paris Agreement, we're trying to keep warming below 1.5 or perhaps 2 degrees, and we're approaching that point more and more quickly. Just to say something now about how rainfall intensity actually links to this rise in temperature. Kevin Trenberth, who is obviously going to be the second speaker today, has looked at this a lot over the last couple of decades at least, and he published a landmark paper in 2003. And there's something that we use in atmospheric science that's called the Clausius-Clapeyron relationship. And that is a relationship between temperature and the specific humidity of the atmosphere. And that relationship says that, and you can see that on the diagram there, for different relative humidities, you get an increase in the atmospheric moisture content with temperature. And that means that a warmer atmosphere holds more moisture, and that's fundamentally the case. And also that for every 1 degree rise in temperature, it increases by about 6.5%. And Kevin looked at this in some detail in his paper in 2003. And because extreme rainfall occurs when the atmosphere is saturated, we expect that extreme precipitation intensities should actually increase at temperature at approximately the Clausius-Clapeyron rate. And because of the energy constraints of evaporation, total precipitation will increase at a slower rate. So your mean rainfall increases at a slower rate than this, and therefore there must also be changes to frequency and duration of rainfall. So the important point to take away from this slide is that a warmer atmosphere holds more moisture, and that this increase will be about 6.5% for every degree rise in temperature. You can see this here again from the 1.5 degree report from the IPCC. And this shows the increase in heavy precipitation with temperature rise for 5-day rainfall in South Asia. And you can see again, it's quite a linear relationship with global mean temperature. And we can see some potentially significant rises there in relation to historical past. But climate change won't only affect the, I suppose, peak intensity of the storm. It will also, as I've said already, affect the frequency and the temporal structure. And of course, that will have knock-on effects on flooding, both flash flooding, which we've seen more of in recent years from these very intense convective storms, which is what I've done a lot of research on in the last 8 years or so, but also on these big, I suppose, tropical cyclones or rainfall that comes from cyclonic systems that are perhaps becoming longer lasting as well. But I've got a few slides on potential changes to storms. So there's been quite a bit of work, and I've just picked out one example here on potential changes to the temporal profile of storms. So you can see here that these authors looked at different storm events and they cut them up into time slices, and they looked at the most intense part of the storm as compared to the weaker parts. And they found that with temperature rise, that most intense part of the storm represented in red there gets more intense at the expense of that weaker part. So it might be that that weaker part just becomes weaker, or it might be that the storm actually becomes slightly shorter in duration. But that you see that intensification in the storm core. In other work looking at changes to storm size and intensity with warming. And this is some work that was done over the United States and by some people that work at the same institution as Kevin, actually. And they looked at taking composites of current and future storms from climate model simulations. And they found that there was an intensification of the storm of about 15% or 20% in the core, but the storm also increased in size. And that, of course, gives you a multiplicative effect. And actually you end up with 2 times the rainfall volume, because you get an intensification of that core there that you can see in panel B in the middle, but you can also see that it's bigger as well, much bigger. And actually that increases the actual volume associated with that storm. And so I wanted to finish by just mentioning tropical cyclones, because I know that Kevin's going to talk about this as well. But there was quite a bit of work done after Hurricane Harvey in the US on this. And obviously I've said already that we're living in a 1 degree warmer world, and I'm sure that Kevin will mention this as well. But that actually affects all of our current events, as well as obviously the potential for bigger changes in the future. And some work done by some authors in the US and Europe on Hurricane Harvey suggested that global warming had intensified the rainfall associated with Harvey by about 18%. And they did this by actually running a climate model with current conditions. And then they also ran a climate model by taking away the climate signal, the sort of warming signal that had happened so far. And they looked at the difference between the two to actually work out how much the impact of global warming the effect that global warming had had on the rainfall associated with Hurricane Harvey. They also found that it had made stalling or more likely, and there's been a lot of work as well recently on the slowdown or the potential slowdown of these big storms with global warming, and that seems something that's quite likely and seems to be happening already as well. We're already experiencing these highly extreme events in a 1 degree world, and therefore we really need to be thinking about how bad these can get if we move to 2 degrees, or even potentially 3.5 degrees, which is where our pledges for the Paris Agreement take us at the moment. I'm going to finish there. We can share slides with you afterwards. But of course, this has a knock-on effect on flooding, and a lot of processes are being enhanced that can then cause increased flooding. And of course, something that I haven't talked about yet is potentially the increased compound flooding from intense rainfall and storm surges. And that's perhaps something that hasn't really started to happen yet, but something we need to be thinking about in the future as well. So thank you very much. And I'll stop sharing.